Let's go ahead and prove this geometric interpretation of the dot product. We're going to use the law of cosines for that. So the first thing I want to do is actually derive this law of cosines, just so you can see where that comes from. So I have this triangle here that's made up of these vectors A, B, and then that green vector is just going to be that vector A minus B. So I'm going to think about this in terms of vectors. And then I'm calling the angle between A and B theta. So how I'm going to go about proving this law of cosines is I need to get some right triangles in here. So I'm going to drop that perpendicular line here. So I'm going to get this nice right triangle on either side. And then we're going to use our cosine and sine properties as well as the Pythagorean theorem to derive that law of cosines. So now when I drop this perpendicular here, it's going to split this segment A up into two little segments. So I'm going to call the one on the left A1 and then the one on the right A2. And I'm really thinking about those as sort of vectors there. So now I have two different vectors. And then when I'm thinking about the lengths of those specific vectors, I'll put those length bars on. And then let's go ahead and call this this perpendicular line, the one that's perpendicular to A here, I'm going to just call that the vector H because I'm sort of thinking about it as the height of that triangle. Okay, so now I have these two different right triangles I can focus on. On this side, I have this right triangle that has theta in it. And then on the other side, I have this nice right triangle here that has that A minus B as the hypotenuse. And so by using those two different right triangles and relating those, I'm going to be able to get my law of cosines. So the first thing I do, I've got the law of cosines where we're heading down here, just to kind of give you a perspective of what we should be getting. And I notice I have a magnitude of A minus B squared equaling some squares on the other side. So that's kind of like doing a Pythagorean theorem on something that has a hypotenuse of the magnitude of A minus B squared. So let's go ahead and do the Pythagorean theorem on that triangle, on that that nice yellow triangle on that right-hand side. So I'm going to say by the Pythagorean theorem, I get that the magnitude of that A minus B vector, so that magnitude of that hypotenuse, is just going to be equal to the magnitude of that H vector plus the magnitude of that A2 vector. And now what we need to do is we need to use that green triangle we have to try to get these quantities here looking more like the quantities I have on the right-hand side of my equality. And I notice I have things about that angle theta. So let's go ahead and see if we can find H, but then also this A1 in terms of the theta. So I see that cosine of theta is going to be the magnitude of that A1 vector over the magnitude of that B vector, which gives me that magnitude of A1 is equal to magnitude of B cosine theta. And then separately, I have that the sine of theta equals the magnitude of that H vector over the magnitude of B, which means that the magnitude of that H vector is equal to magnitude of B. I'll just put it down below. The magnitude of that H vector is equal to the magnitude of B sine theta. Ooh, I'm sorry. Back in my Pythagorean theorem here, I didn't actually square any of these. That's not good. So let's go ahead and square each of those vectors so we actually have that appropriate Pythagorean theorem. So the magnitude squared of A minus B equals the magnitude squared H plus the magnitude squared A. Okay, now I'm going to go ahead and do a substitution here. I'm going to plug in this magnitude for this quantity and see what we get. So I'm going to get that this is equal to the magnitude of B sine theta. That's just the magnitude of H. So when I square that, I'm going to end up squaring each of those terms. And now I need to figure out this magnitude of A2. But what I can notice is that that magnitude of A2 is just the magnitude of all of A minus the magnitude of that A1. Magnitudes are additive like that, right? The length of the sum, or the length of just the A1, the A2 next to each other is just the length of A1 plus the length of A2. So that means that the length of A2 is just going to be that length of A minus, let's go ahead and use this thing we found for A1 up here, the magnitude of B cosine theta. And so that means that when I square that quantity, I just need to square this whole thing. So I'm going to get that magnitude of A minus magnitude of B cosine theta, that whole thing squared. So I get magnitude of A squared minus magnitude of A times the magnitude of B times the cosine of theta, all times by 2, plus the magnitude of B squared cosine squared theta. So I can put this expression in here for that magnitude of A2 that we had above. So I'll just kind of sneak that in. So I'm just going to say plus magnitude of A squared minus 2 magnitude of A magnitude of B cosine of the angle in between plus magnitude of B squared cosine squared theta. Now here you might be recognizing that I have these terms that have both this B squared cosine squared theta and a B squared sine squared theta. So if I take those two terms together, here and here, I'm going to get magnitude of B squared sine squared theta plus cosine squared theta. And then I still have the plus magnitude of A squared, and then minus 2 magnitude of A, magnitude of B, cosine theta. Sine squared plus cosine squared theta is 1, so that goes away. And we get exactly what we wanted, that the magnitude of A minus B quantity squared is equal to the magnitude of B plus the magnitude of A minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle in between. So now we've derived that law of cosines. Okay, now that we have this, we're going to change this to dot products. So we need to recall that the magnitude of some vector squared is equal to that vector dotted with itself. So anytime I see magnitude squared, I can replace that with the vector dotted with itself. So A dot B, we go back, A minus B dotted with itself, dotted with A minus B, so a vector dotted with itself is equal to A dot A plus B dot B minus, I'm going to keep this the way it is, 2 times the magnitude of A times the magnitude of B times the cosine of the angle in between. Now, on this left-hand side, I'm going to use my distributive property. So I'm going to say, do out this distribution with something like a FOIL. So I get vector A dot A minus B dot A and then minus A dot B, and finally plus B dot B. So that's just doing out this distribution, and that should be equal to A dot A plus B dot B minus 2 magnitude of A, magnitude of B, cosine of the angle in between. And now if we look on both sides here, we'll notice that we have magnitude of A, we have A dot A, so those can cancel. We have B dot B, so those can cancel. And so if I combine things, I just get 2 times, we saw that there is a nice commutative property. So having B dot A and A dot B is the same. So that's minus 2 times B dot A is equal to minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle in between. And so if I cancel my minus 2's, again, I can use that Commutivity, to switch the order around, to say that A dot B is just equal to the magnitude of A times the magnitude of B times the cosine of the angle in between. And that's how we can use that law of cosines, which we derived, to prove our geometric interpretation of the dot product. So you don't need to necessarily be able to walk through this step by step, but it's good to see that it comes from somewhere. You do need to make sure you remember this formula at the bottom here. We need to know that this is the geometric interpretation of that dot product. You'll see that in some of the homework questions and quiz questions, exam questions, so make sure you do know that.